Hi everyone, this is Mrs. J, and today we're going to be solving systems of inequalities, and we're going to talk about optimization using linear programming. I have a quick warm-up for you guys, so please pause the video and give it a try. All right, so go ahead and check your work. A few key phrases to always look for. If you see something like no more than, it's going to be less than or equal to. At least would be greater than or equal to. We have another at least here. And then these two are just simple equations because it's just modeling what the cost or revenue is actually equal to. And notice we're multiplying the cost per item by the number of items, which is C and B. And for revenue, it would be the selling price per item times the number of items they sell. So we talked about solving a system of equations before where we graph our two linear equations and we look for that point of intersection. But now we're solving a system of inequalities. So this is when we have a set of two or more inequalities with the same variables. And our solution, which we call a feasible region, is actually going to be the intersection of the shaded regions. So your answer is actually going to be like a shaded in region on a graph. So it's very possible for your graph to be bounded, like you see in this second example here, meaning it is contained on all sides by an inequality. It's also very possible for your solution to be unbounded, like you see in this first graph. So the solution set is this area over here in kind of this purple color, but you can see that here and here there are boundaries, but it's just going to continue on unbounded in this direction. So again, it's okay if you don't have an inequality on every side of your feasible region. So that's just called an unbounded solution, or it could be completely bordered in, which is called bounded. All right, let's give one of these a try. So remember, when we're graphing inequalities, we want to make sure it looks like slope-intercept form. I'll graph this one in red. We just need to be careful for where we shade and what type of line we're drawing with. So this graph, we can see has a y-intercept at -3 and then a slope of 4. And because it's less than or equal to, we're going to have a solid line. And since it has the less than, we're going to shade everything below that line. So that would be the solution of our first inequality. Now if we look at the second inequality here, I am going to divide both sides by -2. So be careful with that. Remember, when we divide by a negative, we need to flip our inequality sign. So here we actually have y is less than -1/2 x. So this we can graph pretty easily. Our y-intercept is the origin and our slope is -1/2. So for this one, since it's just there's no or equal to, we're going to use a dashed line. So it's a non-inclusive boundary, and again, it's y is less than, so we're going to shade everything below. And remember, since it's a system of inequalities, we are looking for that overlap. So on my iPad, it's pretty nice because when I overlap the two, it actually becomes a different color. But on your paper, you need to make sure that you make it really clear what your solution is, which area is your solution. So make sure you color it extra dark. You don't need to erase the other parts. Just make sure it is clear what your solution is. So you can see that this one is an unbounded solution, and it's this region here in gray in the bottom right quadrant. All right, here we have 3 inequalities in our system. So for this first one, I'll do this one in red. So our y-intercept is going to be 5. And our slope is -4/3. And this one, we are going to have a dashed line like this. And it would be everything below because its y is less than. So maybe I'll just do kind of a lighter shade like this. Okay, for our next inequality, here we can see that our y-intercept is at -2 and our slope is +1. This one will be a solid line because of that or equal to, like this. And for this one, we're going to shade everything above. So it'd be all of this region. And then for our last inequality, this is just when x is greater than 1. So this is actually just going to be a vertical line at 1. It's all the times when your x value is 1. And since it is not inclusive, we need it to be a dashed line. So this one, it's just a vertical dashed line at x equals 1. And since it's x is greater than, when it's just x, greater than means to the right. So it'd be everything to the right of that vertical line. So when you have, especially when you have 3 or more inequalities, it can get a little busy on your graph. And so you have to be really careful that you actually find the area that works for all 3. So we could see that that our solution is actually this little triangular area here in the middle. So again, it's really important that you make it extremely clear what your solution is or where your solution is. So maybe I'll color it in extra dark when I have a lot going on. So something like this. So here you can see that we actually have a bounded solution. All right, I've got one for you to try on your own. So go ahead and pause the video and give it a shot. All right, go ahead and check here. So you can see my top equation, inequality here was shaded above. My middle inequality here, make sure you have that dashed line and shaded everything below. And then for this third inequality, a vertical line at x equals 0 and shading everything to the right. So our solution is this bounded region, this triangular region right in the middle. So now that we know how to solve a system of inequalities, we're actually going to apply it when we do what's called linear programming. So linear programming allows us to optimize a function. And optimizing means finding a maximum or minimum value depending on the context of a problem. And we're optimizing a function that has constraints to x and y that are represented with a system of inequalities. So this is actually a really common real life process that people will do. So to help us optimize our function, this process of linear programming, first we're going to graph the system of inequalities, and then we're actually going to find the coordinates of the vertices of our solution area. So this could be something that either it's really clear what the point of intersection is, or if it's not, we may have to find that point of intersection algebraically. And then once we have those coordinates, we're going to evaluate our function using each coordinate. We're essentially going to plug in the x and y values to see which one generates the maximum or minimum that we're looking for. All right, let's try one together. So here we're going to find the maximum and the minimum values of this function, negative 2x plus 6y, given these constraints to x and y. So first we need to graph this system of inequalities here. So for this one, I'm going to try to do the shading all at the end and just shade my feasible area. So for this first function here, it's just 2 vertical lines, one at negative 2. And one at positive 4, and it would be everything between those 2 lines. And then for this next function, we have our y-intercept at 2, and we have a slope of 1. So it looks something like this, and it would be everything below this line. So we can already see that the intersection of those 2 inequalities would be here. And then we have this third inequality. The y-intercept's at negative 3, and our slope is negative 1/2. So it looks like this. And this one is everything above that line. So it's between your vertical lines, below this one and above this one. So hopefully we can see that our feasible area would be this kind of trapezoid right here in the middle. So since this is a completely bounded area, our maximum or minimum value that works for this function up here, again, this is what we're trying to maximize and minimize, it is going to be one of those 4 vertices. It will always occur at one of your 4 vertices of your solution area. So those 4 vertices would be, we have 4, 6, and then we have 4, -5, and then we have -2, 0, and we have -2, -2. Now from here, we want to evaluate these coordinates in this function. So we can actually just say f of each of these coordinates. And then we are just going to go in and substitute those x and y values right here and here. So if you substitute x with 4 and y with 6, for this first one we get 28. For this next coordinate, we would get -38. For our third coordinate, we would get +4. And then for our last coordinate, we would get -8. So then we look at those values, and then we can see that this would be our minimum value. And we can achieve that minimum value when x is 4 and y is -5. And we could see that our maximum value is 28, which is achieved when x is 4 and y is 6. So this is our max, and this is our min. All right, let's try another one together. So here we're going to try to maximize and minimize this function with the constraints below. So again, I'm going to try to just do all of the shading at the end. So this is when y is between 1 and 3. So those are going to be horizontal lines at y = 1 and y = 3. And it'd be everything in between. So it'd be in this little skinny region right here. And then we have y is less than or equal to -x. So a y-intercept at the origin and a slope of -1. And this would be everything to the left. So far we're kind of constrained in this area. And then for this last inequality, our y-intercept is at 3, so right here, and our slope is 1/2. So it looks like this. And this one is everything above. So it's everything between these lines, above this one and below this one. So it's actually an unbounded area. So it's this area here. So when you have an unbounded area, you're still going to look at the vertices of the points of intersection. So here we have 3 vertices we can work with. So we'll check f of, here we have -3, 3. And that would be this value right here. And then we'll check f of -2, 2. And then f of -4, 1. Now, when you have an unbounded region, what you're going to need to do is you're actually going to need to pick some coordinate just off in this unbounded region. So I'm just going to pick -10, 2. We need to pick something over here to see if our graph actually has a minimum or a maximum. Because it's very possible that it doesn't have a max or min because of that unbounded area. So we kind of pick an arbitrary coordinate over towards our unbounded side to see what that gives us. So if you plug in -3, 3 into this function here, -x + y, we get 6. If you plug in -2, 2, we get 4. If you plug in -4, 1, we get +5. And if you plug in our arbitrary point, -10, 2, we get 12. So we could see that as we kind of move farther and farther off to the left, like if I picked -15, 2, this value would just keep getting larger and larger and larger. So it actually, because the largest value is in our unbounded area, this actually tells us that we have no max, because we could just keep on picking values that have a more negative x value, and this overall value would just keep getting larger. So this function actually has no maximum value, but it does have a minimum value here. So our minimum value is 4, and that occurs when x is -2 and y is positive 2. So you do need to be careful with those unbounded regions, and you do need to check a coordinate that comes from the area where it is unbounded. So now we're going to try an actual like real life application of this optimization process. So this says Katie has a 30 square foot garden where she wants to plant lettuce and cucumbers. She wants to minimize, I'm going to highlight this because it's important. She wants to minimize the amount of water she uses. So we're going to have to create a function that models the amount of water, and that's what we're going to optimize. We want the minimum for that. So it says each cucumber requires 2.25 square feet. So that's for each cucumber. And again, we have a 30 square foot garden, and uses 25 gallons of water over the lifetime of the plant. And each lettuce plant requires 1.5 square feet of space and uses 17 gallons of water. And then we have a couple more constraints. It says she wants to grow at least 4 of each type of plant and at least 16 plants total. So we need to determine what's the optimal number of cucumbers and lettuce plants she should plant to minimize that water usage. So first, let's see if we can create that function. Well, actually, let's define our variables. Let's call x, let's just say x is the number of cucumbers she decides to plant, and let's say y is the number of lettuce plants she decides to plant. So from there, let's make our function that models the water usage. So I'll call that f of x, y. Well, it says that each cucumber, each cucumber uses 25 gallons of water. So it'd be 25x, and each lettuce plant uses 17 gallons of water. So plus 17y. So this is the function that we are trying to optimize and specifically minimize. She wants to minimize the water usage. And again, this represents water usage. But now we need to consider all of those constraints. So the first constraint that we can work with would be the amount of space she has. So she cannot go over that 30 square feet. Now, that being said, she can go up to it or less than it, but it needs to be below, so less than or equal to 30. So the square footage would be taken up by cucumber, which takes 2.25 square feet per plant. So I'd say 2.25x. And the lettuce takes up 1.5, and then you multiply by the number of lettuce. And again, that needs to be less than or equal to 30 because she cannot go more than her garden. She can go less than her garden, but she can't go over 30 square feet. Now, another thing we need to look at is that she says she wants to grow at least 4 of each type of plant. So that means that x needs to be greater than or equal to 4, and y needs to be greater than or equal to 4. And it says that she wants at least 16 plants total. So total meaning when you add them up, it needs to be at least, so greater than or equal to 16. So from here, we have covered all of the constraints. So this would be our system of inequalities, and then we will use that to optimize, again, our water usage function. All right, to help us graph this first inequality, is here. I'm just going to rewrite it in slope-intercept form. So I'm just going to rewrite it down at the bottom here. So we have 1.5y is less than or equal to negative 2.25x plus 30. So this gives us y is less than or equal to negative 1.5x plus 20. So let me just go down 3 over 2. Okay, so it looks something like this. And notice that my x and y axis are only, I'm only looking at the positives because remember, our x-axis represents the number of cucumbers and the y-axis represents the number of lettuce plants. So it really wouldn't make sense for us to have negative values for either of those axes. So again, this first one would be everything below that line. And then we have x is greater than or equal to 4. So that's a vertical line at 4. So like this. And it would be everything to the right of that. And then we have y must be greater than or equal to 4. So that's a vertical or horizontal line at 4. And again, it's everything above that. And then for this last function here, that equation would actually be y is greater than or equal to negative x plus 16. So from 16, we're going to follow a slope of negative 1. And you do need to be really accurate with your graphing here because we are looking for those points of intersection of our feasible region. So I'm going to zoom in here. So again, it's everything above the red line, below the blue line, and then to the right and above our vertical and horizontal lines. So it's actually this little sliver right here. See if I can kind of shade this in. This is actually our solution area. So we're going to look at the vertices of that area to see which one would optimize our water usage function. And this one is a completely bounded area, so our answer will be one of those answers. So we do need to check this coordinate, which is 4, 14. And then we need to check 4, 12. And then we also need to check 8, 8. So if you plug in the points, or the coordinate 4, 12, or 4, 14, we get 338. Again, I'm plugging that into our water usage function here. If we plug in 4, 12, we get 304. And if we plug in 8, 8, we get 336. So remember, for this problem, we were trying to minimize it because she wants to use the minimum amount of water. So that is going to occur here at this value. This is our lowest value. So this is saying that Katie should plant 4 cucumbers and 12 lettuce plants to minimize water usage. And that minimum value, that water usage, if they ask, would be 304 gallons. So that is the minimum amount of water she can use, and she would achieve that by, again, planting 4 cucumbers and 12 lettuce plants. So here you can see like a pretty cool application of using systems of inequalities. It can be extremely useful for helping us to optimize real-world functions. All right, so here I have one last one for you to try on your own. So pause the video and give it a shot. All right, go ahead and check your work here. So I defined X as the number of forwards and Y as the number of defenders. And they want us to minimize the salary that they're paying total. So this function models the salary. So 120,000 times the number of forwards plus 100,000 times the number of defenders. Now we do have these constraints. X plus Y must be greater than or equal to 10. They must hire at least 10 new players. The forwards should be between 5 and 8, and they want between 4 and 7 defenders. So here's my feasible region. So I checked all 5 vertices, and I found that this was the minimum value. So they should hire 5 of each, and the least amount of money they can spend is $1,100,000. All right, that is all for today's video. Thank you so much for watching.